Alright, I'm back again with another video. This is going to be on magnetism. Magnetism. So magnetism is defined as the ability of some materials or objects to attract, repel similar objects and some metals. Now, you need to know the basic parts of any magnet. A magnet has two poles, a north and a south pole, and around the magnet we have a magnetic field. Now the magnetic field is an area around the magnet in which a magnetic force is experienced or exerted. Again, this is just the general shape of the field, right? This is not like it's just to give you an idea. That's all it is. All right. So the magnetic field is the area around a magnet in which a magnetic force is experienced or exerted. Right. Well, I should. Yeah. Good. Now, the magnetic poles are the areas in which the field is strongest. That's it. The areas in which the field is strongest. We have something called lines of flux, FLUS, lines of flux or force. These indicate the shape, direction, and strength of the magnetic field. Shape, direction, and strength. Have I missed anything? Oh yes, the magnetic lines of flux leave the north pole and they enter the south pole of the magnet. And then we have temporary magnets. Temporary magnets. Now you should be able to bluff this one. Temporary magnets are magnets that lose their magnetism fairly quickly over time. And then we have the complete opposite. We have permanent magnets. These are the opposite of temporary and retain their magnetism for quite some time. Now, you need to know two more diagrams. One is for two magnets with opposite poles together. And the other one is for shucks, that's way too close. Alright, so let's go with opposite poles together. North, south, north, south. In this case, the magnetic lines of flux are going to leave this north pole and go straight across to that south pole. It's going to look the field is going to look something like this. No. This is attraction. ATTRACTION. if you look closely, it appears as if the South Pole is pulling the North Pole towards it. On the other hand, when we have south and a north and a south, similar poles together, it appears as if the two magnets are pushing each other away, because that is exactly what they are doing. Dun, 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 dun. Now, this is repulsion. Repulsion. That is because the field lines, or the field lines act in such a way to basically push the two poles apart. This is similar to electric fields, where opposite charges attract and like charges repel. Have I missed anything? No, I have not. Now, magnetism has its applications. One such application is the motor. M-O-T-O-R. Now, it's actually the DC motor, and you're going to see why it's called DC motor a bit later. So let's assume we have a magnet. This is a North Pole. This is the South Pole. And we get a piece of wire. Just a single piece of wire. We bend it like that. Dum, 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 dum. So, time to label. This is our coil. This is our commutator. This is our variable DC supply. Why did I put SY instead of SUPPLY? Good. Now, how it works is real simple. How it works. First off, current flows through coils. Current flowing through coils produces something we call electromagnetism, right? Well, I shouldn't say it causes some. Well, electromagnetism basically is the easiest way to define it. There is a relationship between electricity and magnetism. Current flowing, electricity, can produce magnetism, and magnetism can produce electricity. When electricity flowing produces magnetism, it is called electromagnetism. Best way to explain it. This causes a magnetic field to develop around the coils. And here comes a rule. It's called the right-handed grip rule. The right, R-I-G-H-T, the right hand grip rule, G-R-I-P-R-U-L-E, the right hand grip rule. Now, the right hand grip rule uses the right hand. I know, shocking. If you hold, let's say, think of it as fixing your hand like if you're giving someone thumbs up, but between your four fingers that are curved backwards into your palm, you slide like a pencil or a pen. That pencil or pen represents the conductor. Let me go it over again. You basically fix your right hand like if you're showing someone thumbs up. Now slide a pencil or pen between those curved fingers, those four curved fingers. Now, if that pencil or pen is a conductor and current is flowing through that conductor in the direction your thumb is pointing, your fingers will curl around the coil in the direction of the magnetic field. Right? Let me repeat. So if you hold the conductor, like I said, with the thumbs up thing and slide a pen between the four fingers, if your thumb is pointing in the direction of current flow, the fingers in your hand curl around the conductor in the direction of the magnetic field. I will explain via diagram. Let us assume this is the conductor. Current is flowing so. The magnetic field created around this conductor, right, is going to be in this direction, like that, around the conductor. Alright? If the direction is reversed, direction of current that is, the direction of the field is reversed as well. Shucks, I needed to switch to gray. You could try it. It'll be right. Now, current flows through the coils and this causes a magnetic field to develop. I should actually number these steps because I just realized, yeah. You know what? I will move this back here. So current flows, field develops, and then the next thing happens. Deflection, D-E-F-L-E-C-T-I-O-N, occurs, causing rotation, R-O-T-A-T-I-O-N. And this is what a motor is meant to do. A motor is an electrical device that basically produces rotation. It's in your fan, it is in the little device in your phone that causes vibration, it is in electric vehicles. It's just a motor. So let me number these steps for clarity. This is 1, this is 2, excuse me, this is 3. Now, there is another rule. Yes, there is the right-handed grip rule that will never go away, that will stand forever. The second rule you need to know when it comes to motors is the is Fleming's left-hand rule. Now, it's simple. It's not complicated. It is not rocket science. Fleming's left-hand rule involves your left hand. Now, how you go about this is point at somebody with your index finger. For those of you who don't know, your index finger is the finger between your thumb and middle finger. Alright? If I need to tell you which finger is your thumb and middle finger, oh, you're in trouble. With your left hand, point straight ahead of you with your index finger. Now stick your thumb upwards like if you are showing, like if you're pointing a gun at somebody. Right, so this is your index finger. This is your thumb. And you stick your middle finger out to the side. And this is Fleming's left hand rule. Yeah, that's it. Hold on, that's not all of it though. Each finger means something. Right? Each finger means something. So the index finger represents the direction of the magnetic field. F-I-E-L-D. The middle finger represents the current. And this represents the direction of motion. What Fleming said was really simple. He said that if you put a current carrying conductor in a magnetic field, this little law of his would help you determine the direction in which the conductor would move. So index is field, this is current, and this is motion. Alright, that's it. Now, where am I going with this? Let's go back to this diagram here. And let's try to draw it. Yes, draw it. Let us assume the magnetic field is always, well, we don't need to assume. Magnetic lines of force always go from North Pole to South Pole, which in this case would be from left to right. Now, we can represent a wire in the magnetic field, right? Just by drawing a simple circle. Not complicated, just a circle. If current is coming towards us or out of the page, we put a dot. If it's moving away from us, it's an X. If it's coming towards us, it's a dot. If it's coming towards us, it's a dot. If it's moving away from us, it is an X. So let's say, for the sake of argument, right, that current is coming towards us here. Using Fleming's left hand or motor rule, we can determine the direction in which this conductor would move in a magnetic field, or the magnetic field. I'm sorry, but this color is just bothering me. Good. Much better. So, what direction would we get using Fleming's left-hand rule? Well, our middle finger in this case, which indicates the direction of the current, should be pointing towards us. You should be looking at the tip of your middle finger. Your index finger should be pointing across from left to right. And my thumb, at least on my left hand, is pointing upwards. Now, if we, just for the sake of practice, switch the direction of current around to move away from us, you literally have to move your hand around. Alright, you might look like you're having a stroke, but you have to move your hand around. Your middle finger should point away from you. You should be looking at the back of your hand. Right? You should be looking at the back of your hand in this case. Your index finger still pointing from left to right. And your thumb is pointing, at least my thumb. I keep saying your thumb, my thumb is pointing down. So this is DC motors. This is it. This is everything you need to know. Now, usually they ask you, like, how do you make the motor spin faster? Well, there's three things you can change. Just three things. You can change the magnetic field strength. You can make the field stronger. That's the first thing. The second thing, you can increase the current in the coils. And the third thing, you can increase the number of coils. And these are the three things you could do to make it stronger. I sound like Palpatine, but anyways, for those of you who don't know Palpatine, it's a Star Wars thing. I'm sorry. Yes, it's a Star Wars thing. But this is how you make it, or you make the motor spin faster, or rotate faster. How to make it faster. Now, this brings us to the end of this video. In the next one, I have to go over the electromagnet. I kind of realized I skipped that. And I have to go over the, well, not go over, I have to teach the generator, the AC generator, and the transformer. And that should be the end of that video. The last video I'll make for the night is logic gates, and that would be the end of Elec and Mag. As always, share, like, subscribe, comment, and I'll see you in the next one. Bye bye.